Morning. Today we are going to discuss the topic on action angle variables, which is an important concept in the classical mechanics. Now, using action angle variables, we are going to find the frequencies of a periodic system. Now, for this, let us take a conservative periodic system with 1 degree of freedom. Now, we can define the Hamiltonian H as a function of generalized coordinate p, generalized momentum small p, and the total energy alpha 1. H of qp equal to alpha 1. Name this equation as 1. Now solving this equation for the generalized momentum p, we will get p as a function of the generalized coordinate q and the total energy alpha 1, which is equivalent to E. Now for a periodic motion, we introduce a new variable j, which is replaced by alpha 1 as the transformed constant momentum. And this variable j is called the action variable or phase integral, and this action variable j will be defined as j is equal to integral over p dq, where the integration is over a complete period. Now, the dimension of the variable j has the angular momentum. So, from the equations 2 and 3, we see that the j is a function of alpha 1. Actually, from the equation 2, we see that p is a function of q and alpha 1. From the equation j, we say that it is a integral of p and dq. So therefore, p is a function of alpha, therefore j is a function of alpha 1. Now we can define alpha 1 is equal to h is equal to Hamiltonian is expressed in terms of the action variable j. So name this equation as 4. Alpha 1 equal to h is equal to h of j. Next we define the Hamilton characteristic function w as w is a function of generalized coordinate q and the action variable j. Now the generalized coordinate conjugate to j is called the angle variable small w. Actually what we are finding, we are finding a generalized coordinate which is conjugate to the action variable j, and this is called the angle variable w, and this angle variable small w is defined by the transformation equation w is equal to dou w by dou qj. This represents we are differentiating the Hamilton characteristic function w partially with respect to the action variable j, and we call this equation as 6. So in terms of w, the characteristic function w and the action variable j, we can write the Hamilton's equations are w dot equal to dou h by dou qj. This is a function of j, v of j, namely call it as v of j, and j dot equal to minus dou h by dou wi. In terms of angle variable and action variable, small w is the angle variable and j is the action variable. Here we are writing the Hamilton's equation of motion for the angle variable and the action variable. So generally we know that suppose q and p are the generalized coordinate and generalized velocity. The Hamilton equations are q dot equal to dou h by dou pi and p dot equal to minus dou h by dou qi. So that formula we have applied for the angle variable small w and action variable j. Now here v of j is a constant function of j only. Now we are integrating the first equation of the 7 we will get with respect to t. So while we are integrating w dot, you will get w, and v into t plus beta is a constant of integration. Name this equation as 8, w equal to vt plus beta. Now the angle variable w is obtained by the differentiating characteristic function w partially with respect to the variable j. So we will get the generalized coordinate q as a function of the angle variable and the action variable. So now combining this result with equation 8, we get the solution connecting the generalized coordinate t and the time generalized coordinate q and time t. Next we are going to obtain the physical interpretation of the constant v. So here v represents the frequency associated with the periodic motion of the generalized coordinate q. First we are consider a change in the angle variable small w when q goes through a complete cycle of the periodic motion. We define delta w equal to integral dou w by dou q into dq. So this is the change in the angle variable we are finding. Then substituting the angle variable small w equal to dou w by dou j in the equation 9, we will get delta w equal to integral dou by dou q of w is replaced by dou w by dou qj of dou j into dq. This can be written as dou square w divided by dou q dou j into dq. Name this equation as 10. Here the j is constant, so therefore the derivative with respect to j can be taken outside. So therefore we will get the change in the angle variable delta w equal to dou by dou j of integral dou w by dou qj into dq. But we know that dou w by dou j equal to p, so therefore we replace it by dou w by dou qj by p replace பண்ணிக்கிறோம். Now therefore delta w equal to integral dou by dou j of integral p dq. But we know that we defined that j is equal to integral p dq. So therefore delta w will become dou by dou j of j. So we are differentiating j partially with respect to j, we will get 1 as the answer. So thus we see that the angle variable w changes by unity as the generalized coordinate q goes through a complete cycle. This is the physical interpretation of the. Next, suppose if tau is the period for a complete cycle. Now with the equation w equal to vt plus beta, we find the value of the change in w, delta w equal to v into delta t. Since beta is constant of integration, it will vanish. So therefore finally we will get delta w equal to v delta t into v tau. Name this equation as 12. Now combining from the equations 11 and 12, in the equation 11, we see that delta w equal to 1. But in the equation 12, the same delta w equal to v tau. So therefore equating the equations 11 and 12, we get v tau equal to 1, from which we can find the value of v equal to 1 by tau. So this is the physical interpretation of v we are going to we have found out now. Suppose the Hamiltonian is determined as a function of j, the frequency of the motion can be determined by using the formula W dot Hamilton canonical equation W dot equal to dou H by dou J and J dot equal to minus dou H by dou Pi. Thus, we can get the frequency of the periodic motion without solving the problem completely. And it can be obtained by finding the Hamiltonian as a function of J and then taking the derivative of H with respect to J. So, first we obtain the Hamiltonian as a function of J and then we differentiate with respect to J, we will get the frequency of the periodic motion. Now the variable J has the dimension of the angular momentum and the coordinate conjugate to angular momentum is an angle. So hence we call it as angle variable. So now actually we have found out the frequencies of the periodic system for 1 degree of freedom. Suppose the system have more than 1 degree of freedom, what will we do? So now here the application of the angle procedure to system of more than 1 degree of freedom requires the concept of the multiply periodic system. Here in this case we are considering the simple periodic system. When the degrees of freedom is more than 1, we consider the multiplicity periodic system. Now here in this case the motion of the system is said to be periodic if the projection of the system point on the each coordinate qi, pi in the plane is periodic. Thank you, students.